Chemistry. We're about to begin a fairly long unit called Advanced Atomic Theory, where we're going to take a deeper dive into the structure of the atom and how it bonds. And this first lesson is on basic waves. So a wave is a movement of pure energy through space. A medium is a substance with mass that carries the wave. A wave can require a medium to carry it. So examples, and an ocean wave uses water to carry energy. So we often think of when we see a wave in the ocean that it's the water that's the wave, but it's actually the energy that's making the wave move. That's really what the wave is. The water just happens to be the medium. Sound waves are carried by air, water, or solids. So if I were talking to you in the classroom and there was mysteriously, magically no air in the room, you would not be able to hear my voice. You would not be able to hear any sound because there would be nothing to carry the sound wave. Some waves can travel without a medium. Examples are electromagnetic waves can travel from the sun to the earth through outer space where there's no air or other medium to carry them. And this is the type of wave we're really going to be talking about in this unit, our electromagnetic waves. We will focus on electromagnetic waves in this unit. There are two basic types of waves, transverse waves and longitudinal waves. Transverse waves move up and down as they travel from left to right. So the direction of the energy is from left to right. But that could be a spring, for example, or a piece of rope that you wave up and down. And if you tied a little red ribbon to any piece of that rope, the red ribbon would just be going up and down, up and down, up and down. However, the energy of that wave that you're shaking up and down, that rope, is going to be moving from left to right. Longitudinal waves, by contrast, move back and forth as they travel from left to right and require a medium. So these are compression waves. Generally, waves need some type of matter to carry them. This matter is called a medium. This medium could be in the form of a rope, so the example I just gave, a spring, or air particles, in the case of sound waves. In this unit, we will only deal with transverse waves. Here are the parts of a transverse wave. Down there, first of all, you see the central axis, and that goes from left to right, and the wave crosses that. That's what the word trans means. It means a cross. So it moves across that central axis. That's what transverse means. Crest is the top of the wave that you see there. The wavelength is the distance between two crests. It could be between any point on the wave and the identical point on the next wave over, but it's much easier to visualize just the crest. So it's from crest to crest. So it's measured in the units of distance, such as meters, micrometers, nanometers, things of that nature. A cycle is a movement of a wave from one point to the same point on the next wave. So if you see that red line, that's one cycle. So what's the difference between a wavelength and a cycle? Because they both go from one crest to the next. The difference is that a wavelength is actually a measure of distance measured in some form of meters, whereas a cycle is just a number. It's how many times does the wave go down and come back up again. So that would be a cycle. Amplitude is the height of the wave from the central axis. So you see that over on the right side. It's not from the bottom of the wave, which is called a trough. It's from the central axis to the top of the wave. Okay, so we're going to study a wave here. You're watching a transverse wave that is moving to your right. So you're where the boy and the girl are there. You're standing above a crest labeled A when your watch reads 0 seconds. 1 second later, the wave has moved to the right, and you're standing above crest B. During this time, 4 cycles passed you, so count that from crest A to crest B. It starts at A, it goes down and up one time, down and up a second time, down and up a third time, down and up a fourth time. That's 4 cycles. Don't get confused by counting the crests. If you can't start at crest A and count over, you count 5 crests. But it's 4 cycles. It's the movement of the wave from one crest to the next. Frequency is the number of cycles that pass a point each second. So 4 cycles passed you and it took 1 second. So that's 4 cycles per second. That's the frequency. Now we express that in 3 different units of measure. One is called a hertz. The other is 1 over seconds, and that's really the base unit that I like you to use is 1 over seconds because it allows you to do unit cancellations with frequency. The other 2 don't. But if you remember your math, 1 over s, 1 over anything can be expressed as s to the minus 1 power. That's 1 over s, so it's the same thing. So all 3 of those, hertz, seconds to the minus 1, and 1 over seconds, are the same, and they're the unit of measure for frequency. Note the 3 different ways the units for frequency can be expressed. Period is the amount of time it took 1 cycle to pass a point. The period is the reciprocal of the frequency. In other words, you just take the frequency and you flip it over. So period, which is designated as capital T, is 1 over frequency. So it's 1 over for 1 over seconds. And if you do the fraction math on that, you get 1/4 of a second. The 1 over s on the denominator flips over, and it becomes 1/4 second. So period is a measure of time. How long does it take one of those cycles to pass you? The relationship can be seen below. If it takes 4 cycles, 1 second to pass a point, then each cycle takes 1/4 of a second. So there you see the frequency of 4 hertz. So it's 1/4 of a second to go between those 2 crests, another 1/4 of a second between those 2, another 1/4 of a second between those 2, and another 1/4 of a second between those 2. So the period is 1/4 to go between any 2 crests, 1 cycle. And if you add that up, that's 1 second. So that's 4 cycles in 1 second. Period is 1/4 second. In this unit, we will only deal with a special type of transverse wave called electromagnetic waves. Common examples of electromagnetic waves are all energy from the sun, including light and heat. Energy going into and out of an atom is in the form of electromagnetic waves, and that's really the one we're interested in this unit. Waves that a cell phone sends and receives from the cell tower, and X-rays used by doctors and dentists. In this unit, we will be studying the energy that enters and leaves an atom. This energy is in the form of electromagnetic waves. In this unit, we will be dealing with electromagnetic waves. All electromagnetic waves travel at the speed of light, which is 2.998 times 10 to the 8th meters per second. Often we'll just call it 3 times 10 to the 8th meters per second. The speed of light is represented by the letter c, lowercase c. So that's not a variable when you see c. It's a fixed number. It's 3 times 10 to the 8th meters per second. Electromagnetic waves can have an electrical part and a magnetic part. These travel together as shown in the diagram on the right. So the magnetic field is at a right angle to the electrical field, but they travel together. You really don't need to understand that detail about electromagnetic waves. It's just pointing out why they are called electromagnetic waves. The electromagnetic waves do not require a medium. This is why the Earth receives energy from the sun through the vacuum of space. A vacuum is a place where nothing exists, not even air. So if electromagnetic waves required a medium, something to carry them, such as air, they would not be able to reach the Earth, but they don't. And that takes care of our lesson on basic waves, and this we'll build on this in about the next 2 weeks in this unit.